Okay, how's everybody doing today? Doing good, doing great. What I want to go ahead and do today is just kind of wrap up the lesson that we're currently on. I want to go ahead and do another vector projection problem with you, and maybe go ahead and do a couple more problems on the homework, give you time in class to finish that up, and then in the last 5 minutes we'll go ahead and grade it, get it turned in, and then tomorrow we'll go ahead and have our test. That way I can pass back the homework, you can have that to use on your exam, all that good stuff. So there are only two problems on your assignment that have you working with a vector projection. Okay. Would you like to do number 10 or 11? 10.
11.
11. Okay. Okay. Now this one, they're saying the projection, well, you got V and W, so the fact that they're changing the names of the vectors changes nothing. We might have to alter the formula a little bit to fit these, but all I want to do is project V onto W. We're on number 11 on the homework. Okay. Now, normally the formula, if you have U and V, was to go ahead and take the dot product of U and V over the magnitude of V squared times V, right? So we're just going to go ahead and change this up a little bit because I'm projecting V onto W. The formula I'm going to have here, remember we call that W1, is V times W over the magnitude of W squared times W. See, I followed the exact same formula. I just replaced U and V with the vectors that I have now. Okay. Remember, just like finding the angle between two vectors, unit vector, they're just formulas. Hello, man. Come on, man. All right. So let's go ahead and see what first the dot product is. So V times W. So that's going to be, now, does anybody remember what we call those when they're in terms of I and J? Well, now, we want to put it in component form. It's called some kind of combination. It starts with an L. Linear combination. Okay. So remember, we just go ahead and use these coefficients here. That's A, that's B. So V is actually 2, -3. Okay, what would the component form of W look like? 1, 2. There we go. So the first part of the formula, I just want to go ahead and multiply these together. So 2, -3 times 1, 2. And how do I multiply vectors?
A, B, B.
There you go. A times A, B times B. Okay. So it looks like I'm going to have a 2. -3 times 2 is -6. And then remember, we always add the products together.
-4.
So it looks like I'm going to get a -4. Okay, so I have the dot product of the two. Okay. Now, normally when we find the magnitude, remember that's the square root of A squared plus B squared. But if you're finding the squared magnitude, that is just A squared plus B squared. Yes, the square kind of removes the radical. So for W, okay, A is 1, so 1 squared, plus B is 2, 2 squared. So 1 plus 4 will give me 5. Okay, so finding those two items, the dot product and the squared magnitude, oh, forgot my square right here, that takes care of this portion. That creates your scalar. Okay, so the dot product was -4 over. We found the squared magnitude to be 5. Now all I want to do is multiply by W. 1, 2. So that's the last part of the formula right there. Now remember, if you have something outside of component form, well, we just go ahead and distribute, right? And if it helps you, to go ahead and put it over 1, that's fine. So let's see, what's -4/5 times 1? -4/5. And I want -4/5 times 2. -8/5. Okay, so that is your vector projection. That right there is W1. Okay, so again, it's just a formula, nothing to it. Okay, that's what you do. That's it. Now, the instructions say, let me take a look at this right here. It says for 10 and 11, we found the vector projection, but then it says the vector components of U orthogonal to V. Now, there's that key word again. Orthogonal means they form what angle? Right, 90 degrees. There we go. Right. Okay. So the orthogonal, the perpendicular vector, we always call that W2. Well, as we saw yesterday, we know that the original vector, in this case, V, the one projecting onto the other, whoa, that was weird. We know it's going to be W1 plus W2. Well, vector V was 2, -3, right? So I'm going to go ahead and plug in 2, -3. W1 is the vector projection we just found. Okay, that's the formula. So I'm going to go ahead and say -4/5, -8/5 plus W2. W2 is that perpendicular one that we're looking for. Okay, so all I have to do is just rearrange this equation. Would everybody agree that W2 would equal 2, -3 minus -4/5, -8/5?
Yeah.
See, all I did was just subtract that group over. Okay. So now a little bit of algebra and the problem is done. Okay. So what am I actually going to subtract from 2? Yeah. So adding or subtracting, just look at the corresponding values. So I want to take 2 over 1 and I want to subtract a -4/5. Okay, well let me go ahead and change that. What happens when you subtract a negative? You add it. Okay. Now what is the common denominator? 5. So I got to multiply this one by 5 over 5. So it looks like I'm going to have 10/5 plus 4/5. So that'll give me 14/5. Okay. Now I'm going to do the same thing, but with the b values. So -3. And I'm going to subtract -8/5. But it becomes addition as well. Again, common denominator would be 5. So -15/5 plus, that's a plus, 8/5. Oh, now be careful. It's going to be negative, but negative what? -7/5. Okay. So that's what I'm looking for. So W2 would equal 14/5, -7/5. There we go. So that's exactly what you're going to want to do on number 10. A has you using the formula to find W1, the vector projection. Part B has you doing this to find W2. Yes, I can actually do number 7 and 8. No, I just used this space to write. This is not number 12.
Okay.
Okay.
I was like writing it halfway through 12 too, and I was
Yes,
just
it's
like,
not number 12. Okay. This is not number 12. I was just using the space because I already used. Yeah, so this one right here, that's part A. This one right here was part B. Those are the 2 answers for 11. Mm-hmm. There we go. Okay. Now, let me go ahead and quickly show you this graphically, just so you can kind of have an idea, because I did provide you those sheets yesterday, those half sheets that had all the vectors on there. So let me, actually, no, it's in this one. Okay. We did not get to that. I'm just going to go ahead and show you very quickly. You remember how we're going to go ahead and take a vector and we're going to rewrite it as its some of its component form, creating a right triangle? Okay. Well, I just want to go ahead and show you graphically like what we're trying to find. Every time you project, in this case, U onto V, if you project one vector onto another, okay, W1 is the vector projection we're looking for. The other one's the perpendicular vector W2. Well, to kind of give you an idea, there's an easy way to think about this. Pretend that the vector being projected onto is the ground. Okay? So V is going to be the ground, right? Directly above the ground, go ahead and draw the sun.
Wait, okay. Can we do this on here?
Yes, that little half sheet that I provided you. Okay? So you'll notice if the sun is directly above this vector U, it's going to cast a shadow down onto V. That's what we've been finding that we call the vector projection. What you would expect to be the shadow, that's what the formula gives you. That's W1. So wherever he stops, if I now go ahead and connect it there, that perpendicular one, that's W2.
So which way would? So W2 could be a tree.
W2 could be a tree?
Yeah, like a casting a shadow.
Could be, yeah. W2 is always perpendicular to the ground, the vector you're projecting onto. So the point of this right here is just to kind of show you it doesn't matter, how the two vectors relate to each other if you draw them, okay? The shadow is the vector projection. So here you'll notice V is still the ground, right?
Yeah.
But where would I put the sun? Say it one more time, Brent. There you go. Because remember, I'm going to always put the vector U between the ground and the sun. So here I would put the sun here. Okay. So this right here, the shadow being cast, that's W1. Okay. That formula that we use, that's what it's providing you. Okay. So W2 is the perpendicular one. Okay.
Why do we make the sun wear sunglasses?
Now, I'm not worried about, really showing you these graphically. I just kind of wanted you to get an idea. If you were to look at it graphically, the vector that we're given, that's what we're finding. Okay. All right. Would you like me to go ahead and take the problem that we were just looking at and show you?
How is the sun for that one?
Well, because, see, you always have to put U between the ground and the sun because I'm projecting U onto V. Oh, so this one here?
Yeah.
Okay, so here I would put the sun right here because the shadow would be cast here. That would be W1. Okay. Yes, now here's the thing. In order to find W2, you would actually have to translate this vector over because it always has to be perpendicular. Now that would be W2. Okay.
So like would this be put together?
Bottom right.
Okay.
What's happening?
Now the bottom right just shows if the vector projection happens to go in the opposite direction. Okay. So for example, I can actually use this sun for this diagram right here. If the shadow casts straight down, then that would be W1. And in fact, W2 is always perpendicular to it. Okay. And if that is a little confusing to you, don't worry about that. I just wanted to go ahead and show you that graphically, just to make a connection. No, I'm not going to have you responsible for that. I'm just going to have you work on the formula. I just wanted to go ahead and show you in case anybody was interested. And who wouldn't be, right?
Yeah.
Yeah. Without a shadow of a doubt.
Okay.
Okay.
Wait, so where would the sun be on that last one? Yeah, it would be.
Oh, but actually, the way I set these two diagrams up, the sun would be below the upper one, but it would be above this lower one. So I could actually use the same one for both diagrams. There you go. Okay. All right, so like I said, if you're not okay with that, that's fine. I'm not going to expect you to graph those. The only thing I'm going to be expecting you to do is be able to use the formula. The projection of U onto V is U dot V over the magnitude of V squared times V. Actually, I don't believe I did. I think on the test I used U and V. Mm-hmm. Stick with the same letters. Okay. All right. I'm sorry? Oh, sure. I mean, you've already got it on your notes, but if you want to write it again.
Yeah.
Okay. All right. So what other question on the homework would you like to look at? 7? 7 and 5. Okay. All right.
Okay, never mind on 5.
So never mind on 5? Okay. So let's take a look at 7.
Why does 7 look like that?
Now, 7, it's actually given it to me as a linear combination. So this one's kind of unique. What it wants you to do here is find the angle theta between the two vectors.
Did you use the unit? I used the unit circle. Is that,
Okay.
Does that help?
Oh, absolutely. You can absolutely do it that way if you want. Now remember, when you want to find the angle between two vectors, this is the formula we have. Cosine of theta is equal to, does anybody remember the formula?
Wait. Oh, is it like the 2 times sine?
Oh, no, you're thinking about an identity.
What?
I'm talking about the formula to find the angle between two vectors.
Oh, like the.
Do you guys remember it was u dot v over the magnitude of u times the magnitude of v?
Yeah. Oh.
Okay. So there's my formula. Now, on number 7, I actually probably wouldn't suggest using that formula because there's a better way to do it. Why don't I work number 6 with you, and then I'll show you number 7, the little shortcut.
I did.
You want to do that? You want to? Oh, well, let's see if you got it right, which I'm sure you did. Now, what is the component form here for 3i plus j?
3 plus.
Okay, so v is equal to 3, 1. W would be -2, 4. Okay. And again, they're using v and w, doesn't change anything. My formula would be cosine of theta is equal to v times w over the magnitude of v times the magnitude of w. Okay. So let's go ahead and figure out what the dot product is. So v times w. Well, let's see. 3 times -2, -6. 1 times 4, 4, and then I'm going to add them up, so I get -2. Okay, so I've got the dot product so far. Now I want the magnitude of v, so this one I do need to keep the square root. So the magnitude of v is the square root of, oops, forgot my equal sign, a squared, so that would be 3 squared, plus b squared, so 1 squared. So it looks like we have the square root of 10. So I've got the magnitude of v. So I only need one other part, and then I could use the formula. So I need the magnitude of w. So this is the square root of, and we're still on number 6. So a, that would be -2 squared, plus b squared, 4 squared, square root of 20. Now this is the one time we won't worry about simplifying the radical if you're finding the angle between the two vectors. I would just leave it like that. So I need these 3 items put into this formula right here. Now we are going to have to do what to cosine? Yeah, so cosine inverse of, well, the dot product was -2 over the magnitude of v, the square root of 10, times the magnitude of w, the square root of 20. So that should give me theta. We just got to figure out what that is. So let's see here. Cosine inverse, control divide. Let's see, we have -2 over the square root of 10. Get out of there, times the square root of 20. Okay, so I'm getting 98.1. Okay. So I'd say there's 98.1 degrees between the two vectors. There we go. So about 98.1 degrees. So I believe I did put a problem or two on the test tomorrow where find me the angle between two vectors. That's exactly what you'll want to do. Okay. All right. Any questions on that? No? Now, the reason number 7 is different, Genevieve already pulled out a unit circle. We could absolutely go ahead and do that. But this one, there's kind of a shorter way because you'll notice, what are they providing you? Yeah, the radian measures. What quadrant would pi over 6 be in? First one. So let's say this, is pi over 6, right? Okay. And the other one, 3 pi over 4, would be in second. Oh, because remember, as you're going around the unit circle, remember you start at 0, then you have pi over 2, then you have pi, so 0.75 pi. There we go. Okay. All right, so that is 3 pi over 4. What the problem is wanting me to find is what's the angle measure between them. Okay. Well, don't you already have the values you need? Yeah, all you got to do is subtract them. So that's why this one's a little different. You couldn't do that on the previous one because you weren't given any angle measures. We had to use the formula. So I want to take 3 pi over 4, and I want to subtract pi over 6. And we can change them to degrees, or we could work with the fractions.
It's 105 degrees.
Okay. Because what is the degree measure of 3 pi over 4?
135.
135. Minus pi over 6 is 30. So she's absolutely right. That is 105 degrees. Yeah. Now, even if you were to run through the formula that I just showed you on number 6, you would still get the exact same answer. But that one, I don't think it's necessary to do all that extra work when you can just subtract the two measures.
And if we did, wait, actually, yeah. Okay, so say it's cosine pi over 6, right?
Okay.
Okay.
Uh-huh.
So if we get the x of pi over 6 minus sine, like, is that another way? I mean, it's...
Yeah, you actually could go ahead and write those using the values. So if you remember the triangle here,
Yes.
pi over 6 was 30 degrees, right?
Yes.
So this is 30, this would be 60. Now remember, on the unit circle, that was 1. Across from 30 was 1/2. What was across from 60? Square root of 3 over 2. Okay, that's a 3. So cosine of pi over 6 would be square root of 3 over 2. So u could be square root of 3 over 2, sine of pi over 6, 1/2. So you actually could use the values to get component form and then go through the formula. But yeah, like I said, that's just way more work than what we just did there. And then you can do the same thing. But remember, at 3 pi over 4, that's when x and y were identical. The only difference was a sign. One was negative, one was positive, because it was in the second quadrant. All right. So what I'm going to go ahead and do there, I'm going to stop, let you guys finish that up. If you haven't already done so in the last 5 minutes, I'll go ahead and put the key up, we'll grade it, and get it turned in. Okay. All right. So if you have a question, let me know.